The demand for fresh water is increasing at a rate far greater than the environment can sustain. While 71% of the Earth's surface is made up of water, the majority is salty oceans, leaving just 2.5% fresh. Of this tiny fraction, we are only able to access about 30%, as the rest is tied up in glaciers and snow cover. Although 1 in 10 people around the world do not have access to clean drinking water, the greatest global use currently is for creating energy. For example, in 2010, nearly half of the 35.5 billion gallons of water used in the United States per day was used to produce thermoelectric power. Even here at UConn, we used to use millions of gallons of drinkable water to power turbines in the cogeneration plant on campus. In order to reduce stress on local rivers, the university turned to reclaiming its wastewater to instead create the necessary quality for energy purposes. One of the essential steps in this process is a forward and reverse osmosis system. Forward osmosis utilizes an osmotic pressure gradient for desalination across a semi-permeable membrane. A highly concentrated draw solution flows over one side of the membrane, while a lower concentrated feed solution flows across the other. This induces a net water flux from the feed to the draw solutions in order to equalize the osmotic pressure. On the other hand, reverse osmosis operates by applying a pressure greater than the osmotic pressure to the concentrated solution. This forces water molecules through the membrane, leaving contaminants behind. The first step is to calibrate the conductivity probe using several concentrations of salt water. Then, prepare 1 liter of 5 molar sodium chloride stock solution using a stir plate to mix well. While the solution is mixing, turn on the chiller, making sure the water level is adequate. Next, fill the draw and feed tanks, each with 2 liters of deionized water. While wearing gloves, gently remove the CTA membrane sheet from the solution. It will need to be cut to an appropriate size, so measure by carefully placing one end of the membrane into the cell. The orientation of the membrane is important and distinguished by a rough and smooth side. Gently identify the sides and place the membrane into the cell with the rough side facing down. Be sure that it fully covers the inner O-ring but does not touch the outer one. Then, replace the top half of the cell. Place washers and nuts on the bolts and tighten with a ratchet or wrench to ensure a watertight fit with no leaks. Turn on the pumps and set the flow to 1 liter per minute, then set the pressure. We chose to vary the pressure with trials at 3, 6, and 9 psi to observe the change in salt and water fluxes. Measure enough stock solution to obtain the necessary concentration in the draw tank. We also decided to vary the concentration of salt in the draw from 0.5 to 1.5 molar. Once the software signifies that the data has reached equilibrium, add the solution and test the conductivity. For reverse osmosis, we will be testing 3 different membranes, SW30, BW30, and NF270. Carefully remove the membrane and determine the orientation. Wet the cell with deionized water before placing the membrane shiny side down. Place the top back on the cell along with the washers and nuts for a watertight seal. Fill the tank with 9 liters of distilled water and set to the desired flow rate. Again, we are varying pressure using 100 and 200 psi, which is set using the gauge. Then mix a concentrated 1 liter sodium chloride solution to bring the feed tank to 2,000 parts per million of salt water. Take a sample every 10 to 15 minutes from the permeate lines over the course of 1 hour. Record the flow rate and conductivity. In order to draw conclusions from the experiment, we performed several calculations to analyze the data, including JW, the water flux, JS, the salt flux, A, the pure water permeance, and B, the solute permeability. To calculate the pure water permeance, we plotted the water flux against osmotic pressure, where the slope represents the A value for each trial. The solute permeability was determined by graphing the salt flux versus change in salt concentration. The salt flux was heavily affected by changing the salt concentration in the draw. This can be attributed to the resulting increased osmotic pressure. Here, the water flux was plotted against the transmembrane pressure in order to calculate the permeance. We can see that the NF270 membrane had much greater water flux than both the SW30 and BW30 due to the greater slope. The slope of the data in the salt flux versus concentration graph represents the solute permeability. Since the slopes are nearly zero, the change in concentration barely affected the salt flux. Of the variables tested in the forward osmosis experiment, we can conclude that changing the pressure has no effect on the system, while changing the draw concentration greatly affects the fluxes. In reverse osmosis, each membrane had different properties, with BW30 being the best in terms of minimizing salt flux while maximizing water flux. However, the NF270 had the greatest overall water flux. Increasing the pressure also increased the overall water flux over all the membranes.